Lastly, I want to talk about rolling friction. This is the least important type of friction. And the reason that I keep stressing that is that in the past, when students have read through the sections of the book about friction and I ask them what questions do they have, they all ask about rolling friction. So I'm stressing that this is the least important because if at the end of the video you feel like you understand everything except rolling friction, you're actually doing okay. So the idea of rolling friction is that your wheel is moving, but the surface is stationary. And this is a little hard to think about, but imagine a tire traveling through mud. You clearly see the tire tracks in the mud, as if each portion of the tire was just pushed down stationarily. Another way to think about this is imagine taking a roll of toilet paper and rolling it across the ground. The toilet paper itself, once it hits the ground, is stationary, but the circle part is in fact rolling. So that's kind of what's happening here. So it's a different category than either static or kinetic because the surfaces are technically stationary, but the wheel itself is moving. The important thing to realize is that it's very small. So in many cases where there are wheels involved, we actually say that friction is negligible. So that's pretty important. Where this will matter is when we talk about propulsion in another series of videos that I guess comes next. And so in this case, it's helpful to recognize that rolling friction is actually acting backwards. So rolling friction acts backwards compared to how the wheel is turning. And again, you can just think about this as the surfaces are momentarily stationary even though the wheel is turning. Now I want to do some comparisons between the two main types of friction, static and kinetic. First, a little bit on coefficients of friction. There's a table in the back of your book. It's also found in chapter 6, but if you have a physical copy of the book, flipping to the very back cover might be easiest. You can also find values online. Something to be careful about is depending on what source you go to, you might find different values. So this is a case where if you're looking up coefficients of friction for a weekly problem, make sure to say what website you use to get your coefficients of friction. I think there's a physics reference book online that has a lot of them. Wikipedia will be fine as well. So what's important to recognize is that you need two surfaces, right? There are two surfaces interacting, and what's happening microscopically depends on both surfaces. So whenever you look at your coefficients of friction, it will say one thing on another. So wood on wood is different than wood on snow, or ice on ice is going to be different than, say, metal on ice. So this is a fairly short list, but I think all of the problems coming out of the book will probably only use these. Don't feel like you need to memorize these. If I ever give you a test problem, for instance, that requires coefficients of friction, I would give you a small table to the side, or I would just tell you explicitly what values to use. So one thing to note when you look across this table is that your static is first and then kinetic. And note that these values are decreasing in every single case. So I'm saying that kinetic is typically lower for normal surfaces like that. That's true. So static friction is actually higher than kinetic friction. And that will be important for the plot that we're going to talk about next. Note that your rolling friction is much, much, much smaller, and it isn't even defined for some things. We don't normally think about wood rolling on wood. So because these are so small, that's one of the reasons why we usually consider rolling friction just negligible. So the last thing is that some problems may simplify by saying these values are equal to one another. For some things like rubber and dry concrete, 1 versus zero point 0.8, those are not exactly equal. Same for 0.3 versus 0.25, but it's a simplification we sometimes make. But you should expect to see a higher value for static than kinetic friction. So now I want to get to this plot that I really, really like, and that I think if you understand this plot, you understand friction. So we have two regions in this plot, static friction and kinetic friction. And it's really important to recognize what's on your y-axis or vertical axis and what's on your horizontal axis. This is the applied force. And in this case, we're just thinking about one force that's applied, horizontally, like a nice simple scenario where you have your box and you are, say, pulling, right? And so we have a frictional force of whatever type backwards. So this on our y-axis is the frictional force. So what this plot is the frictional force versus how hard we are pushing or pulling. This is on the horizontal axis push. My picture was a pull, but hopefully that still makes sense, right? I can redraw it as now, if I'm pushing against this, look, it's me pushing, that now we are going to have an F push, and we are going to have, and just in a different color for simplicity, friction backwards. Okay, so we have a region where we have static friction. Then we have a region where there is kinetic friction. This isn't in time, this isn't in space, this is how hard you're pushing. Initially, you push a little bit, your object is starting from rest. You push a little bit, your object stays at rest. Think of this as like trying to push against a heavy bookshelf on carpeting. You can push, you know you're applying a force, but you don't see it accelerate, you don't see it move. What that means is that your frictional force equals your pushing force, right? So what that says is that if I push this hard, I get this much friction out, and notice that they're equal, right? This value and this value would be equal. So friction, static friction in this case, keeps pushing back as hard as you are applying it. That's why you get this one-to-one line here, right? So what this is telling you is exactly what is labeled here. Your frictional force equals your pushing force. So this is that idea that you need to actually look at your free body diagram to understand what's happening. Your calculation tells you the maximum value. So there's a point where you get to the maximum value of kinetic friction, of static friction. And so once you push just a little bit harder, we are now into the region of kinetic friction. And for this plot in particular, we've said that the coefficient of kinetic friction is lower than the coefficient of static friction. And again, that's normally true. And the reason that we can see this happening is that we had this maximum value of static friction up here, but then your kinetic friction is at a lower level. And in both cases, N here is your normal force. So same normal force on your box, just a different value of different coefficient. So what that means is if you are, for instance, pushing right here, this is now your F push. And this is your kinetic friction. Notice that for this point, F push is larger than your kinetic friction force. That means that it's going to accelerate because in your free body diagram, F net will not be equal to 0. So that's what happens when you have a lower value of kinetic friction. And again, in the real world, that's what we normally have. So you push, you push, you push, you push, you push. It doesn't actually start moving. Then it starts moving. If you keep pushing with the same force or just a little more, it actually starts accelerating because you're pushing harder. So please think about this plot, pause and reflect on it if you would like, but I think that this is really helpful to think about the difference between kinetic and static friction and how one responds to how hard you push, how the other one doesn't, and therefore what's going to happen to your object's acceleration as a result. So feel free to pause and examine this. It is in your book, but it's kind of small in the book. This is reproduced from a previous edition of the book when it was a little bit larger. Okay, in summary, the force of kinetic friction depends on the coefficient of friction, specifically the kinetic friction, and normal force. That's how we calculate it. And again, normal force, normal force, normal force. Don't overly simplify this. You should always find what your normal force is explicitly. Static friction, we can calculate the maximum value, but otherwise you would use a free body diagram to find out what the static friction's value is if you're not at the maximum value. Finally, whenever you want to get the coefficient of friction, you need to look at both surfaces, and frequently this value will be different if it's static versus kinetic. And again, the table's in the back cover of your book if you have a physical copy. There's also a table in chapter 6, and you can also find values online.